Hey everyone, today we're looking at section 4.5. This is on graphs of logarithmic functions. There are going to be some examples that we don't do simply because they involve sketching the graphs, and really sketching the graph is just a matter of going to Desmos and typing in the function. So there's, in the modern era, to me at least, there's not a ton of value in hand sketching graphs. So let's go ahead and jump right in here. I have a lot of text for us here so that we can go ahead and look at all of these properties of logarithms in one quick look here. So let's start out by recalling that the exponential function f of x equals 2 to the x, I'm starting at the top here, produces the following table of values. If I plug negative 3 in, I get 1/8, right? Because 2 to the negative third power, maybe I'll write over on the side just for this one. 2 to the negative third power, this is the same thing as 1 over 2 to the positive third power, which is 1 over 8, right? And also, we could say, let's see, 2 to the negative 2 power. This is 1 over 2 to the positive 2 power, which is 1 over 4. So this is how we're getting these numbers that are in the f of x column, right? I'm just plugging them into the exponent. So, because the logarithmic function is an inverse of the exponential function, if I say that g of x is log base 2 of x, then that's the inverse of f of x, which is 2 to the x power. So it's going to produce this table of values that follows, where notice that the table of values for log base 2 of x is the table of values for f of x equals 2 to the x power, but I've swapped the x and y's, right? Because if I find an inverse of a function, that means that I'm swapping the domain and the range of that function. Notice that in this second table, as my input increases, my output increases. As my input increases, my output is increasing more slowly. So at first, I'm increasing by these fractions, right? And I'm getting an increase in the y value of 1. And then I have to increase my x value by 4 over here in order to increase my y value by 1. Because the exponential function only outputs positive values, the logarithm can only accept positive values as inputs. So the domain of the log function is 0 to infinity. Because the exponential function can accept all real numbers as inputs, the logarithm can output any real number. So the range of a logarithm is all real numbers, or negative infinity to infinity. So again, 3 and 4 here just stem from the fact that when I find an inverse, it means that I swap the domain and the range of that original function. And if we were to graph log base 2 of x, notice that as the input approaches 0 from the right, the output of the function is growing very large in the negative direction, right? As I get closer and closer to x equals 0, my function is going downward very quickly. In symbolic notation, we write, as x approaches 0 from the right, f of x approaches negative infinity. So it may be difficult to see the plus sign here. So to symbolize as x approaches 0 from the right, we put this superscript plus sign. F of x approaches negative infinity. That's what that first part says. And as x approaches positive infinity, f of x approaches positive infinity. That's the second part. I think we could probably read that. But of course, it's difficult for me to tell until I actually upload this. And so we have a few features of the logarithms here in this table. Graphically, in the function g of x equals log base b of x, the graph has a horizontal intercept at the point 1, 0. The graph has a vertical asymptote at x equals 0. The graph is increasing and concave down, like a frown. The domain of the function is all x values greater than 0, and the range of the function is all real numbers.